Good morning, and thank you for the invitation. I go on further on Jonas' presentation. There will be some same aspects that come back. I'm the building physical engineer of the project, and I was part of the design team for the energy and the comfort concept. And we did some monitoring during 2 years in the occupied house, and I will show you some results of that monitoring campaign. And I first start with the 7 principles that Lone highlighted on. Maybe first of all, our briefing for the RenovActive was that it should be a comfortable building with a low environmental impact. It should be affordable, replicable, scalable, and robust. So those principles really has driven, has this helped us in making some decisions. First of all, for the RenovActive concept, the first principle is to have a high thermal insulation quality of the envelope. Jonas has told you already. Maybe one adding remark is that the state of the existing house was very terrible. It was an inhabitable space, as well as the house beside. There were a lot of mold problems, and the water tightness of the existing rendering was out of lifespan, so it wasn't watertight anymore. So the walls are fully wet with a lot of mold inside. So that's why it was very important to have external insulation in the house, to have a new render that was watertight, and also to treat the masonry walls of the neighbor to have a watertight facade here, because it is the same wall that is going through from the one building to the other building. If it wouldn't have done that, there would be mold problems in the new house as well. So this is something that comes up with a renovation. So we decided to have a very good U values of the building, like passive house standard. We had triple glazing at the north facade and double glazing at the front facade as the southwest, and the facade, maybe you can see here, is the southeast facade. Then we have the good daylight availability in the house. This is something that already was mentioned by Jonas. Then another important aspect is the ventilation system. If we want to have a healthy building, then the ventilation system is very important. We have here a demand-controlled ventilation system on CO2 relative humidity and VOC for the toilets. The system we have here is a natural ventilation supply system by the window grills above the windows, and we have one central fan for the extraction. There is one Velux active house already built, and there were some complaints about the thermal comfort in the living room. Therefore, we decided here to have some preheating of the ventilation air in this room, and that was shown already by Jonas. So here we have the ventilation grill, and here we have a small convector that can preheat this air, and then with this small gap, it is coming into the house. We think it is very important to have a well-designed system, otherwise the people will block the system. That's also why we have shown here to work with some gaps that the people really don't see that there is a system. But the drawback of that kind of system is that it's that they are not aware that there is a system, so that they are not aware to maintain it as well. So we have to find a trade-off between both aspects. And something else that we have discovered in this project is that commissioning is very, very important of ventilation system to detect initial technical failures, and the quality of the workmanship is in Belgium not really good. If you didn't have here the monitoring campaign, there would have been still some technical failures in the house. It's a weak aspect of the concept. The fourth principle of the RenovActive concept is to integrate natural peak ventilation, so to have a lot of operable windows. Here we have a fully automatically controlled system with the pivoting windows here underneath at the floor levels and at the sleeping room levels. And here we worked with attic roof windows that are automatically controlled. For For the attic, we have a window in this side and in this side of the attic to have good cross ventilation. For all the other rooms, we work with the stack effect of the staircase shaft, where it really enhances the ventilation rate to have good indoor, to have a good thermal comfort. In Belgium, it's important to have mosquito protection, and I think everywhere it's important to have a good burglary protection. Otherwise, the people won't use the natural peak ventilation system. So here we have the pivoting windows, and the control is with temperature dependent CO2 set points. So for temperatures below 15 degrees, it is only used as a peak ventilation system. And for temperatures above 15 degrees, it is used as the hygienic ventilation system. The fifth principle is automatically controlled exterior solar shading. We have the solar shading on the southeast and the southwest facade, but we didn't put it on the north facade. There we find out that for the attic, the summer comfort was not what we expected. And we find out that for the northeast roof window, it was triple glazing. There was an interior solar shading. And at the 21st of May in the morning, we found out that at the bottom it was 45 degrees and at the top 60 degrees. So we had a really big heating panel in the attic room because of the sun. So we decided that actually for all roof windows, an exterior solar shading is really obligatory. Even here we had a little bit of budget problem, but it's really important to have still that solar shading. And then if we have solar shading and we have a natural ventilation system, it's important that the air can pass us by at the sides, at the bottom, and if the openness factor of the screen is high enough to have some airflow through it. The sixth principle is the thermal mass, which is very important. Therefore, it's also important to have exterior thermal insulation and not at the interior. Jonas told us already, it's a lightweight structure inside for the floors and the attic. So we have actually not a lot of thermal mass. And that's why we have decided for this extension to have a higher thermal mass with building blocks and not a building system with with a wooden skeleton, which has a lower environmental impact, but then our thermal mass would be too little. So we decided to have more thermal mass. And the last principle is to have a building automation system, because it really eases the mind of the people. They don't have to think about, do I have to open my window to have a good indoor air quality? Do I have to lower my solar shading because maybe it can heat up later on in the afternoon? The system is really thinking in your place, and it really improves the robustness of the house. We find out that it's very important that the building automation system can, that the building occupant can set his own settings and according to his own priorities, because he can have some primary needs like mosquito protection, burglary protection. And if there is a conflict with the needs of indoor air quality and energy consumption, he would really block off the complete system. And if he can set his own settings, then he can find some good consent for his own needs. It's important to have an override of the automatic control at any time. And also that it returns to the default after override. So these were the 7 principles. And so I told you we did some monitoring during 2 years in the house while it was occupied. Every room had this box with sensors for temperature measurements, CO2 concentration, and relative humidity. And we measured the door opening with this sensor. That was by Raspberry Pis. We also had NetAtmos in every room. And with the Emon Pi, we measured the electricity, the water, and the gas consumption. We find out that the indoor air quality in all the rooms, according to the Active House Radar, was very good. We achieved category 1. Except for the bedroom of the kids, it was category 2, and the bedroom of the parents. For this room, it's because one of the parents slept a lot in the bedroom together with the kids in the bedroom of the kids. So actually the occupation of the room was higher than it was designed for. And then we see that the natural peak ventilation system really helps to have also a good indoor air quality, even if it was not designed for it with the natural supply vent system. For the bedroom of the parents, it's also category 2, and it is just according to the Belgian regulation. This shows a heat map of the CO2 concentrations during 1 year of 2018. This is the days of the year, so yeah, January to December, and this is the hours of a day. We see that the people go sleep very late and from till midnight, and then they sleep till 10 o'clock almost in the morning. So the whole night, the indoor air quality is very good at the living room. And when it's occupied, we can see here that also then the CO2 concentrations stay low. Only some little, yeah, we have some less indoor air quality when there was some high occupation at that time. For the sleeping room of the parents, then we see that the occupation is in that region. And we had an experiment where at the first half of the year, we used the natural ventilation system with pivoting windows only. And at the second half, we used the natural supply vents with the pivoting windows. We see that the indoor air quality was here less good than in that case, but that was just because of the set points of the CO2. So we can also have discomfort with that system. If we look into the heat map of the temperature of the same period here, we can see that here it is much colder than in that winter. And actually the occupant found it too cold here. So actually he preferred to have less indoor air quality and a better thermal comfort than the other way around. And in that way, it's important to have a demand controlled system that it's not always full ventilation rate, because then the draft complaints are higher. So for the indoor air quality, we can say that we have a very good indoor air quality in the house by the ventilation system designed by the Belgian national standards. That the demand controlled ventilation system works well. But for cooking and cleaning, those air pollutants are not recognized by those sensors. And then we see that the occupants are manually opening the windows. In that's good. And I think it's very important, if you have a demand controlled ventilation system, that you have that option to use those windows. If we have a natural ventilation system, we need to meet the thermal comfort requirements, and that we can do by demand controlled ventilation, by temperature dependent set points, like in winter, and also hot spell, I show you later on. And the supplier is preheated by the small convector in line with the window grill. It works for the ground level, the occupant is satisfied with it. And maybe for the sleeping room here, it would have been also a good idea. If we look into the thermal comfort, we see on that heat map that the thermal comfort in the living room for the second half of the year of 2017 was very good, and actually overall it was good. We can have a look into the summer comfort. Here, this graph shows for some days, like we have 5 days, and the temperature outside. We see the outdoor temperature, it's with the blue dots. We see that the temperature rises 20 degrees, 25 degrees. It's a summer period in Belgium. And in the red, we see the attic, where the solar shading system was not working at that moment, and the natural ventilation system was not working. So we see when the system fails, then, or it is shut off, that it's really a problem. So that it's very important to have the solar shading and to have the natural ventilation system. Here, the temperatures were more than 35 degrees. Now we have a look into a hot spell in 2019, in the middle, at the end of June. We had a hot spell with the highest temperature measured ever in Belgium, 40 degrees outside. We see here for the different rooms, the temperature in the house. And what we first see, we can see two things on that graph, is that the difference in temperature between the attic room, the orange line, and the room at the living room at the ground floor, the yellow line, is 7 degrees at highest temperature of the day. And that is just because there is much more thermal mass here at the ground floor level than at the attic. So thermal mass is very important to have a good thermal comfort in during hot spells. And a second thing we can see is here, actually in that house, the temperature increases quite fast after it increases outside. And that is just because we have here the natural supply ventilation system. If we have a ventilation system with heat recovery, then you don't have that increase that fast. During hot spells, actually, we think the thermal comfort is more important than the indoor air quality at that time. And so it's important to have temperature dependent CO2 set points during that time of the year. And that we changed into the system in the automatic control system. Of course, the indoor air quality don't have to be too bad, but we find a better trade-off between thermal comfort and indoor air quality. So for the thermal comfort, we can say we have an overall good thermal comfort. The exterior solar shading on all attic rooms is very important. Its thermal comfort is better at levels with more thermal mass than in the attic. The automatic window control should consider wind speed and not only rain, as to prevent slamming doors. It was something we didn't have taken into account. The energy and the comfort are important, but when there are conflicting primary needs like burglary risk and mosquito bites, the people don't use it. So here in that case, the natural peak ventilation system was turned off during night because there was no mosquito mosquito protection. So the people really prefer to have it too hot instead of having mosquito bites. And then in a hot spell, thermal comfort is temporarily more important than the indoor air quality. And then at last, I want to show you some things about the energy consumption. If we look at the electricity consumption here in the house, we see that the building-related electricity consumption for pumps and fans is only 10% of the yearly energy consumption. For lights, it's 2%, and the rest is 88% for the plug loads. And their electricity consumption is in line with the Belgian electricity consumption for households. Here we have heating with a gas condensing boiler, so that's why the energy consumption for heating is not electricity. If you look into the production of the PV, we see that it's 10% of their yearly electricity production, and the consumption during night and day, and night is in Belgium also the weekends, it's almost 50-50. And we see that 36% of their PV production is injected into the grid. So they have a self-consumption of 65%, yeah. If you look to the criteria of the active house radar, we see for the energy demand, we have calculated 60 kilowatt hours per square meter, but if we measure it, it's a bit more. We have seen that this is because the indoor temperature in the house for the energy performance building calculations in Belgium for housing, we take a mean temperature of 19 degrees. And we have measured here that for the first winter, it was 29. So it was almost 2 degrees higher than for the calculations. And in the second winter, it was a little bit lower. So that is the main reason why there is a big difference. Another reason is that the people close to solar shading due to insecurity feelings. So they didn't want people to see when they were at home and not at home. And that's why they closed the solar shading all the time. So we didn't have any passive solar gains into the living rooms. Another measure of the active house is the origin of energy supply. The more renewable energy you have, the higher your score. Here it was limited because of the gas condensing boil, because it should be affordable. And we think a district heating system is here more in place than a ground source heat pump for every house. There was no place on the roof anymore for PV panels. We think it was more important to have daylight in the attic than having PV panels on top of the roof. So we used PV panels as a garden shed, and those PV panels, they produce like 10% of the energy consumption. And if you look at the annual primary energy performance of the house, we are around 60 kilowatt hours per square meter. This is rather high. It is, but this is because of the choice of not having the gas condensing boiler and of having a natural ventilation system without heat recovery. If we can conclude on energy consumption, we can see that the EPB calculation method is an overall good predictor of the energy consumption. We have an underestimation of the indoor air temperature, and there is an overestimation in the method of the auxiliary energy consumption for heating by 40%. This is for the pumps. We also see that for the demand-controlled ventilation, we have a reduction of 30% of the ventilation flow rate, so that means less heating energy. We have a reduction to 40% of the electricity consumption for the fans, and our mean airflow is only 50 cubic meters per hour, while it is dimensioned for a maximum of 233. So the overall conclusions is that the exterior solar shading on all attic roofs is very important. That demand-controlled ventilation can reduce the energy consumption for heating and ventilation, that it helps to meet the thermal comfort needs, and that not all air pollution sources are detected by those sensors like cooking and cleaning, so that manually operable windows complement the system. That the energy and comfort are important, but if they are conflicting with primary needs, the people block it. So it's important to take that into account also in your automation system. For the hot spells, that the thermal comfort is temporarily more important than the indoor air quality, and systems require maintenance, and the commissioning of it are very, very important. Thank you.
Thank you very much, Friedl, for a thorough account of how did it actually work in practice. I think this is a key part of or element of accelerating the renovation wave. That is to know how did what already took place and was experimented actually work. So thank you very much for sharing in a very systematic way. I think there are a number of papers also accounting for the extensive research work that has been done on the RenovActive. We can share those links to those papers. I think one was presented also last week, as far as I know. So for those of you who are very interested in hearing more and seeing some of the elements more, we can share the links to this